This chart tracks the projected infrastructure of global mobile networks. Legacy 4G deployments are flatlining, while cloud-native 5G is accelerating, on track to run more than 80% of all global networks by 2030. For the last decade, 4G evolved packet cores have operated on monolithic architectures. Telecom functions required dedicated hardware appliances, locking operators into specific vendors and rigid physical constraints. Scaling a network under this model meant buying more physical boxes. It required substantial capital expenditures simply to add capacity, and major network upgrades dragged on through 6 to 12-month deployment cycles. 5G Standalone changes the physical baseline. The specialized telecom racks are replaced by generic commodity data center servers. The core network is no longer a collection of hardware. 5G Standalone dismantles traditional network functions and rewrites them as independent, stateless microservices. Cloud-native 5G is the structural replacement required to protect operating margins as global data consumption surges. This block represents the traditional 4G core. It operated as a single, tightly coupled application where every function was bound together in one codebase. 5G Standalone breaks that monolith down. It isolates the logic into independent functions. The Access and Mobility Management function, or AMF, handles device registration and tracks subscriber locations as they move between cell towers. The Session Management function, or SMF, is responsible for setting up the network barriers and enforcing quality of service for individual data sessions. These specific logical functions are packaged with their dependencies into lightweight, highly portable execution environments, Docker containers. To manage the sheer volume of these containers, operators use Kubernetes as the master orchestration layer. It automatically places containers onto available servers, discovers new services, and continually monitors their health. Because core telecom functions are now software containers, the network is liberated from physical rack space. It can be dynamically orchestrated, moved, and scaled instantly across public, private, or hybrid clouds. This interface shows a Kubernetes cluster currently operating under normal network load, running a baseline of exactly 10 session management function pods. Imagine thousands of subscribers simultaneously entering a stadium and connecting to the network, creating a massive, sudden spike in session signaling load. The Kubernetes horizontal pod autoscaler reads this exact metric, immediately kicks in, and scales the service from 10 pods to 100 to process the surge. When the event ends and signaling drops, Kubernetes systematically terminates the access replicas, returning the cluster to its baseline of 10. That entire lifecycle, scaling up to meet demand and scaling down to conserve resources, occurs without any manual intervention from the network operations center. This efficiency is amplified by decoupled network planes. The control plane, which contains functions like the AMF and SMF, is completely separated from the user plane, which handles the raw data traffic.
Because they are separated, they use divergent scaling triggers. Control planes scale based purely on signaling events, while user planes scale independently based on the actual volume of data flowing through the network. Operators no longer pay to power and cool redundant hardware waiting for peak traffic. Independent plane scaling ensures they only consume the exact compute resources they need when they need them. This diagram illustrates the separation of compute and state in a cloud-native design. Data regarding active subscriber sessions is explicitly pushed out of the compute pods and stored in external NoSQL databases. If a server rack loses power, or an active software pod fails catastrophically in the middle of routing a critical session, the subscriber data is not lost with it. Kubernetes instantly spins up a new instance. Because the architecture is stateless, the new pod queries the database, retrieves the session state, and resumes routing the connection seamlessly. But with thousands of microservices constantly scaling, updating, and dying, ensuring they communicate reliably becomes incredibly complex. The solution is a service mesh. This abstracted software layer manages all routing, load balancing, and circuit breaking across the ecosystem. The mesh provides a zero-trust security environment. It issues cryptographic identities to workloads and enforces mutual TLS encryption on every single exchange between microservices, regardless of their location. It also provides precise control over live traffic. Operators can program the mesh to route exactly 10% of signaling traffic to a new software version, validating its stability before rolling it out network-wide. Stateless data separation and service meshes remove the inherent brittleness of traditional network cores. Operators can push continuous code updates and absorb massive node failures without dropping a single subscriber connection. To understand the economic shift, we have to look at the cost of scaling. In a legacy core, every 100,000 new users require approximately $25 million in proprietary hardware. A cloud-native core handles that same growth with just $10 million in commodity compute and storage. This table models a million-subscriber network transition. Replacing carrier-grade appliances generates a $300 million reduction in initial CapEx. CI/CD automation also changes innovation costs, dropping a 5-year feature roadmap from $30 million down to just $3 million. Beyond these operational savings, the architecture introduces completely new models for revenue generation. This diagram shows native network slicing. Orchestrators partition the shared physical infrastructure to spin up distinct, isolated logical networks, each with its own guaranteed service-level agreements. A critical broadband slice serving an automated factory can guarantee sub-50 millisecond latency and absolute reliability, running concurrently alongside an IoT slice designed for high device density and low bandwidth agricultural sensors. Cloud-native cores transform telecom infrastructure into programmable, multi-tenant revenue platforms. India's massive 5G rollout shows how this plays out globally. Unlike mature markets maintaining legacy coexistence, India holds a distinct greenfield advantage. Regulatory momentum from TRAI actively favors open standards and multi-vendor Kubernetes deployments, allowing operators to prioritize software architectures from the ground up. The implementation roadmap starts with targeted pilot deployments in major geographic circles. Instead of high-risk national rollouts, Phase 1 integrates cloud-native platforms to absorb 5 to 10% of total network traffic. In these early phases, operators are testing enterprise-focused network slicing, providing custom, premium private broadband to major tech and industrial clients. The goals of Phase 1 are strict: validate the automated CI/CD pipeline, ensure absolute uptime, and reduce costs by 20% before scaling outward. Bypassing rigid hardware constraints for automated microservices establishes the absolute baseline requirement for the next decade of global telecommunications. Operators who execute this transition decisively secure the speed and flexibility needed to capture the lucrative innovation margins of 5G and 6G. Legacy holdouts face rigid scaling costs, delayed service rollouts, and an irreversible operational disadvantage.